So here's video number 2 of the Acid Base and Buffer Lab. What I want to show you in this video is how we can create a buffer simply by adding KOH, a base, a strong base, to vinegar. Now we're going to generate something what's called a titration curve. At least that's what I'm going to attempt to do. I have my tap water here. I have my solution of potassium hydroxide. I just threw a bunch of solid KOH into distilled water. I didn't really measure it. I just know that that's basic enough for this to work. And I have a cup filled with a small amount of vinegar in this styrofoam cup. One way we can measure pH, besides using a pH probe, as you can see I've calibrated it so it's reading pH 4. One other way we can do it is the more approximate way of demonstrating is to use this pH paper. So it's just an orange colored paper, and it changes color. The scale runs from red for pH 0 up to dark, very dark blue for pH 13 or 14. So if I put it into tap water, it's going to read, didn't even really change color. Maybe turned a little bit green. You can't really tell in the video. So yeah, that's about pH 7. If I dip it into the vinegar, this is in a weak acid, so it turns sort of a yellow-orange, so pH 3 or 4 according to this. If I dip this paper into this KOH, it should turn a very dark blue or dark green color. And you see that it clearly does turn a very dark blue. So we know that that's a very basic solution. That's an approximate way of getting the pH of a solution. This pH probe that I'm using is the best way to do it, a more analytical way of doing it, quantitative, so to speak. So what I'm going to do here is first I'm going to demonstrate how tap water has no buffering capacity at all with this pH probe. So what I'm going to do is I have on this screen, like I had in the other video, I'm graphing pH as a function of time. I'm just going to drop in base into water in trial 1, and then I'll add base to vinegar in trial 2. Try to do it at the same rate and see what happens to the pH. So let me take my pH probe and rinse it off, first in my clean water, and I'll put it into the tap water, and as the pH paper predicted or said, it should be around a pH of 7. You can see the pH is pretty rapidly rising. So what I'm going to do, let me have that stabilize here. Just give it a minute for the pH probe to adjust. It's going up. As you saw in the other video, it's interesting that tap water actually is closer to pH 7 than distilled water, which is the opposite of what I thought I would see, because I thought distilled water is pure water, so it should have a pH exactly 7. The distilled water I bought is around a pH of 5.5 to 6, whereas tap water is around, as you can see on the screen, is 6.34 and rising. If I left it long enough, it probably would rise up to close to 7. So let's just start the collection. I'm going to start, and we'll get a baseline for the pH. You'll see it start to come out here. So water, tap water, isn't really a buffer because it's just a mixture of the vast majority is water, and there's a very, very small amount of the hydronium ion and a very, very small amount of hydroxide ion. So it is not a buffer. So it should have no resistance to the change in pH when I add acid or base. So I'm just going to add a solution of KOH to this water. Just give it another few seconds here to get a baseline here. So I have my pipette here for the base, and let me just drop some base into here. I'm going to add 1 drop of base and see what happens. I'll just add 1 drop of base to this mixture and see what happens to the pH. It went up a little bit. Actually, it's going up quite a bit. You see how it's spiking all of a sudden now that the OH is mixed into the solution. Let me add another drop. 1 drop. Put that in there. Swirl it around. pH is, with 2 drops, it's gone from about a pH of 6.4 up to pH 9.23. Let me add 1 more. I'm guessing that the concentration of this hydroxide solution is around, oh, 2 moles per liter, so it's concentrated enough. So you can clearly see that water does not have any buffering capacity. Adding in, a couple more drops of base is causing the pH to go almost to the limit. Very, very high. So let me just add about 3 more drops to that. See what happens. The pH is up to already almost 11. So I've added about 10 to 15 drops of KOH to about 100 milliliters of water. So water clearly has no ability to resist change in pH, as we would expect. So let me rinse off my probe here. Let's put it back in the buffer solution to make sure it's reading correctly. I better stop that because I wanted to. So ignore that drop in pH. So the pH rise you saw is right here for pure water. I'll clean up this graph and put it on the report a little bit later. So now what I have is just about, 50 milliliters of pure vinegar right out of the bottle. And what I'll do, I'll move it over here a little bit so you can kind of see what I'm doing here. I think you can see that here. Good. Maybe if I did that over here, you could see it. Yes, it doesn't matter, I guess. So what I'll do is I will add my KOH to the vinegar. So let me move this here. And let me take the probe out, rinse it off here. Okay. Let's put it in the vinegar. Now we would expect vinegar to have a pretty acidic pH. As you can see, it's dropping down to 2.6 something. So that's what we expect. Let's start the data acquisition. First, let me save this previous run, store latest run. We'll start data collection. So now we're down here around 2.61. So how is this going to demonstrate a buffer if I'm using vinegar? Well, that's what I want you to think about for the questions I'll ask you in the lab, but I'll give you a few pointers here. So right now in this solution, all we really have is a mixture of vinegar molecules. So that's, depending on how you want to draw it, it's going to be CH3CO2H. The acidic hydrogen is attached to an oxygen atom. You've seen me draw the structure of vinegar many times, or acetic acid, I should say. Or you could write it as HC2H3O2, indicating that it has one acidic hydrogen. But it is a weak acid. It's not like hydrochloric acid. We can consume vinegar in food, and it doesn't harm us. So it's a very weak acid. It's got a Ka of about 10 to the negative 4th or 5th power. It's very low. The Ka of HCl is 1,000 or 2,000, so that tells you how weak this acid is. It just supplies very few protons to the mixture. So now what I'm going to do is I'm going to stir this with my right hand, or just kind of gently swirl it. And now I'm going to add KOH, the same solution I added to the tap water there in this trial here to show you the huge spike in pH. And let's see what happens. I'll just start pipetting it in. I'll go at about 1 or 2 drops a second. You can see the pH is going up a little bit here, 283, 286, 285, 292, 296. It's going up a little bit. Let's keep going. But you can see that it is not going up as fast as the pH changed for when I added this KOH to pure water. So it's the reason why it's not going up so fast is because I'm actually creating a buffer as I add the KOH. So how does that happen? That's what I want you to try to figure out. So the reaction that you would think about or write is aqueous potassium hydroxide, KOH, plus vinegar, so not vinegar, but acetic acid, which is the molecule that's reacting. Vinegar is mostly water, but you can see that the graph is pretty flat right now. But anyway, so it's KOH aqueous plus HC2H3O2, which is the formula for acetic acid, would give me potassium acetate. It's the same reaction that we ran in the last lab where we were titrating vinegar. So I'm really doing the same reaction. I'm titrating vinegar, acetic acid with KOH, but now I'm giving you a visual picture of the titration. I'm not worried about counting drops or detecting the exact equivalence point. What I'm hoping to show you here is are two things. Why this is a buffer. We're in the buffer range right now. You can see I'm adding a lot of base. Look how the pH changed the pH. Look how the base that I added to the water drastically changed the pH of the pure water with this other graph. With this graph, you can see that there's only a gradual increase in pH as I'm adding in quite a bit. I'm dropping in about 1 to 2 drops of KOH every second. I'm not sure. I think you can see this on the video. It's still running. Good. I'm trying to do things that were two hands. It's kind of, but all right. So here we go. So this is called the buffer region of this titration. Now we didn't talk about titration curves in class in the videos, but this is what I'm generating in a somewhat crude way, because in one of the classes that we teach, we actually give students an unknown weak acid, could be vinegar, and we ask them to figure out which acid it is. And you can do that if you do a careful titration curve where you carefully measure the volume that you're adding. I'm just counting drops. And you carefully go through the equivalence point where you'll see that large rise in pH. Well, I'm not seeing that right now. I'm not seeing a spike in pH because I now have a buffer solution simply by adding in KOH to vinegar. So, what's going on again? What's going on is KOH is reacting with acetic acid to give me the conjugate base of vinegar, of acetic acid, which is potassium acetate. But you got to remember that at the beginning of this titration, I had a lot of acetic acid molecules in this cup. And so as I added in the base slowly, as I'm doing here, those acetic acid molecules are slowly being converted into the conjugate base, which is potassium acetate or acetate ions. The potassium ions are just spectator ions. They're not doing anything. And I'm also making water molecules. So now that I'm starting to create a large number of acetate ions, which is the conjugate base of acetic acid, I'm making that's a buffer. A buffer is a weak acid, acetic acid, and a relatively equal amount of its conjugate base. So that's why this pH, as you see, is not changing. It's going up slightly. It's up to 4.18, but it's not going up super fast like it did when I added KOH to pure water. This is a demonstration of how a buffer works. I'm in the buffer region of the titration curve. So let me pick up the pace here and see if we can get through the equivalence point here in this video. If it's taking too long, I'll stop the video. I will finish the curve and then start up the camera again and show you what I got. So I'm just going to continue to add base to this. I might even have to extend the time that I run this titration. I ran it out to 900 seconds, which is, what is that, 15 minutes. So if you want to, I'm just going to keep going and filming here. If you want to fast forward and just kind of watch the curve in fast forward speed, you can fast forward to the point at which I'm going through the equivalence point. Let's just keep going here. I'll pick up the pace with adding base and see if I can. So you can see that the pH is starting to go up rapidly. When you get close to the equivalence point, the pH will all of a sudden just shoot through the roof. It'll go through a steep rise, and if I rush this, I'll miss it. It'll just look like a vertical line. So I'd like to be patient and try this and get it right. I've got to be careful here. And I also want you to think about what would the pH be when I have completely neutralized the acetic acid molecules with this KOH I'm adding. So that isn't hard to do. You just have to think about the balanced reaction. When I've reached the equivalence point, I've added as many molecules of KOH as acetic acid molecules that were there. So they've neutralized each other, and what am I left with? At the equivalence point of this titration, I'm left with potassium acetate, acetate ions, and a bunch of water. Well, acetate is the conjugate base of a weak acid. So the pH of a ion that's basic, acetate ion, should be above 7. If I do this titration with a strong base and a strong acid, if I were adding KOH to HCl, at the equivalence point I have a mixture of sodium chloride, or I'd have a mixture of KCl and water. If the reaction were KOH plus HCl, the products are KCl and water. So at the equivalence point of a strong acid, strong base titration like that, you just have a weak salt and water, but the salt is the conjugate acid and base that make up that salt have no pH altering ability, so the pH of that solution is 7. Here I'm making a conjugate base of a weak acid, so this conjugate base acetate ion is a relatively strong base, which means that the pH, it has enough of a basic strength to pull a proton off water and make hydroxide ions. And I want you to think about that reaction. I'll ask you about that. What's the reaction that produces hydroxide ions that will cause the pH of this solution at the equivalence point to be above 7? So again, you have to imagine that acetate ions plus water give you hydroxide ions and the parent acetic acid molecule back. It's sort of like writing the reaction I'm doing right now, acetic acid plus KOH in reverse. So you can start to see that rise in the pH. We're getting closer here. Let me start adding it a little faster here. Oh, now it's starting to spike. Maybe I'm going through the equivalence point. Looks like I'm getting close. I might have to extend the collection here. Yep, now it's starting to rise up. So now I'm out of the buffer region. So now I've added so much OH that I've completely consumed, there we go, it's going through it. I've completely consumed the acetic acid that was there. There we go. I kind of got lucky there. You can see the pH is kind of leveling off, but it's jumping up a little bit. So I rushed it a little, but you see the point. You see that now that I'm going through that equivalence point, I've destroyed the buffer, and now all I'm really doing is adding OH to the solution and making a more basic solution. And it eventually will level off. Even if I keep adding this KOH, it can't really go above pH of I don't know, 12 or 13 or so. You can see it's kind of leveling off. I'm at pH 12. Let's just keep adding some and see what happens. I'm going to extend the time here. Hopefully it'll let me do that. Experiment. Extend collection. Good. It's letting me do that. Let's keep swirling. Adding. So again, when you're watching these videos, I realize you don't want to sit here and watch me stir a beaker for 20 minutes. You're going to have to kind of fast forward and kind of rewind and pick up everything. But you should be picking up the fact that what I just generated is a titration curve of the addition of a strong base to a weak acid. This is a titration curve, which I could use this curve to identify that this unknown acid, if I wasn't told it was acetic acid, I could figure it out. Looking at this region here, this is the buffer region. You notice that it took a lot of time to change the pH. I was adding many, many drops. I was adding many drops of KOH in that region, and you can see the pH didn't change much. That's because in this region I had a buffer solution, and now I don't have a buffer solution. Now at this point right here, I've completely neutralized the acetic acid molecules with KOH, and then from here on up, I have just excess KOH. So now I'm just making it more basic. But notice that right about halfway there, what's the pH? It's around 8.5 or so, which is about right. It's above 7. The pH at the equivalence point of a weak acid, strong base reaction, titration, is above 7. I know I've said that a few times, but I don't want you to miss it in case you're skipping around the video. At the equivalence point, I have a conjugate base of a weak acid, the acetate ion, and water. And the acetate ion is a strong enough base that it can actually pull a proton off water and produce hydroxide, which a small amount of them, so means that the pH is above 7. So let me just add a few more and then we'll stop this video. So I'll ask you some questions about the reactions that were occurring at different parts of this video, and I'll also put this titration curve in the report and show you. Okay, let me just add one more, and then we'll end it. As you can see, the pH I'm adding quite a bit, and it's not going up that much. You might think, well, do I have a buffer solution now? No, because the pH isn't changing. No, I'm just at such a basic solution that I don't have enough KOH to change the pH any higher. That's not a buffer solution. This is a buffer region. This is the buffer solution region. I'll stop it there. So to quickly summarize, again, in this region I have a mixture of acetic acid molecules and the conjugate base, which is potassium acetate. And an equal mixture of acetate ions and acetic acid is a buffer solution. And that's why it resists a change in pH. The pH change here is less than 1 unit over a large region of addition of strong acid KOH. So buffers do have the ability to resist changes in pH. But then I eventually added so much KOH that the buffer was destroyed. And now I just, at this point, I completely neutralized all the acetic acid molecules, and now I have just, all I have left are acetate ions and excess hydroxide. And the excess hydroxide is what causes the pH to rise so much, because it's a strong base. All right, this will end video number 2.